If we are thinking of managing any waste, metallurgical or otherwise, it is an unwritten rule, at least according to me, it is unwritten rule that two aspects of this waste need to be clearly understood. One is its chemical composition, the other is its physical feature or something equivalent to that of its mechanical feature. In the previous session, we had an overview of, we considered what chemically constitute a blast furnace slag, and we also understood how the way we cool the molten slag changes its arrangement of molecules and consequently renders a different mechanical properties to these slag. So in this session, we are going to get into the ways we can profitably manage this particular metallurgical waste. Now, depending on how we cool the blast furnace slag that gets generated out of this iron making operation, we get these three forms of slag. So when you air cool the slag, we end up having crystalline slag. On the other hand, if you choose to water cool it or spray cool it, we either end up having glassy or the granulated form of slag. And in the example, the anecdotal example that we considered, it is the granulated slag that is being sold for a price. Now in this session, besides considering what is the prominent or the predominant way in which the blast furnace slag is being managed, in addition to that, we will understand why is it the granulated slag that is sold for a price, not the crystalline one or the glassy one. So essentially, the properties that are rendered by the slag, in addition to the chemical composition, is going to be based on the amount or the nature in which the molecules are arranged. And we see that one form of blast furnace slag is being sold, and they have explicitly specified it. So we are going to understand why it is the granulated blast furnace slag that is preferred over that of the other form of slag. And while we are doing so, we will understand the dominant way of managing the blast furnace slag. The amazing aspect of managing the blast furnace slag is that on one hand, we have a waste that is getting significantly generated. The amount of it getting generated is enormous. So that is exactly what we saw in our previous session. So if you have missed it, I encourage you to just look into that aspect. The amount of blast furnace slag is in no way minimal. The amount that it gets produced is significantly higher, and it is in future, in the days to come, it is not going to decrease. That's what the projection says, the scientific projection says. So if we have to find a way to manage this blast furnace slag, it should not be just it's compatible with the chemical composition and also the physical nature of the blast furnace slag, but it should also take into account the amount of this waste that is getting generated. We can have an application wherein these two exactly match, that is the chemical composition and the mechanical behavior exactly match in an application, so we can directly use our blast furnace slag there. But if that application characteristically operates on a minor scale, if the amount of requirement of the blast furnace slag in that application is low, it is no longer profitable to us because the amount of blast furnace slag that is getting produced is significantly higher. So therefore, we need to come up with an application, or we need to come up with a usage of the blast furnace slag wherein the usage significantly increases as the amount of blast furnace slag also increases. So they need not be correlated, the causal need not be correlated, these two need not be correlated. But if we find an application which is also increasing as much as the amount of blast furnace slag is increasing, so it is essentially a match made in heaven. So one such match is the construction application of the blast furnace slag. If you have heard of the blast furnace slag, at least just if you skim through any book on iron making, towards the end of the iron making, you will have a chapter or two on managing the blast furnace slag, and there it would have been stated that these blast furnace slag are used in construction or building application. So what the reason is primarily because of the chemical composition and also their mechanical properties. But one hidden advantage of using blast furnace slag in the construction is that as the amount of cities, modern or otherwise, as they keep on expanding, what they essentially mean is, what they essentially translate to is the infrastructure, the building keeps on increasing. So as they keep on increasing on one end, we have on the other end the amount of blast furnace slag, they keep on increasing. The amount of steel that we need to produce in order to cater to that particular expansion of city also increases. As a byproduct, our slag is also increasing, and now we have found a home for the slag with or in the building sites, in the construction applications. So essentially we have something close to a match made in heaven, wherein we can take our blast furnace slag and place it, and the scale in which the blast furnace slag is getting generated is almost equivalent to that of the scale in which we are expanding, we are constructing our building. So as far as the amount of the waste that is getting generated in the blast furnace operation, we have a way to manage them in the construction sites. Now, when we focus on one form of the blast furnace slag, that is the crystalline blast furnace slag, the way we can deploy it in a construction site is in the form of concrete. So concrete, it essentially comprises of these four components. We have fine aggregate, coarse aggregate, cement and water. So if you narrow it down, we have aggregate, cement and water, and these three essentially constitute a concrete. Now the substance to the concrete, so if you treat the cement as the binding agent, of course in this context, if we treat them, we can refer to cement as in numerous ways. In this context, if we treat them as a binding agent, the substance, the strength that is offered by the concrete essentially stems from that of the aggregate. So the substance to the concrete is provided by the aggregate. Now this aggregate are essentially minerals that are found on the surface of the earth, and they are purchased for a price. So when I want to build or manufacture concrete, if I want to fabricate a concrete, I need these three components, and one of the component is equally priced with respect to that of the other. So if I'm purchasing cement, I also have to purchase aggregate. Now given the chemical nature and also the mechanical feature of the slag, the blast furnace slag, it is possible for me to replace these aggregates with the blast furnace slag, the crystalline blast furnace slag. So what replacing aggregates with crystalline blast furnace slag does to me as a consumer is, first thing, it reduces the price of my concrete. So I need to spend some money, relatively more amount of money, if I want to have a concrete that is exclusively made of aggregate. Now what we are doing is we are replacing the aggregate with the blast furnace slag, so the amount of aggregate I need to purchase decreases, so thereby reducing the price of my concrete. This is from the economical perspective. Now when you consider from that of the environmental perspective, now I have found a home for my blast furnace slag, so I don't have to essentially worry about how to manage this blast furnace slag. Now my concrete is the home for me. Now if you consider an example, so if you are generating steel to cater to a construction site, you own a blast furnace and you are operating the blast furnace solely for the purpose of extracting iron, which can be catered to the construction site. In addition to catering the steel, now you are catering the waste as well. So you are doing away with the waste as well. So you are essentially producing some money, you are generating some money, you are producing some economy from the waste as well. So this is in a way referred to as the circular economy. So this is a prime example of the circular economy. So in addition to supplying them with iron, with steel, you are also supplying them with waste, which can be used to replace the aggregate, thereby helping them economically and also helping all of us environmentally. Now, when we want to understand what are rather the drawbacks of it is compatible, or can I use the blast furnace slag in the place of my aggregate, one feature that needs to, or one property that needs to be satisfied by my blast furnace slag if it is replacing my aggregate is the strength of the concrete that is formed at the end of it. So if I have a concrete wherein some portion of my aggregate is replaced with the blast furnace slag, I need to ensure that the strength is comparable to what is expected when my concrete is completely made of aggregate. So there was an extensive study wherein different grades of concrete were fabricated. In one end of the concrete, it was completely made of aggregates. On the other hand, we have a concrete that is completely made of blast furnace slag. And now the compressive strength, the most important physical or mechanical property of the concrete was measured for all these grades of concrete. So we have 4 different grades of concrete. On one extreme, the concrete is purely made of aggregates, so a 0% blast furnace slag. On the other end of the spectrum, we have the aggregates entirely made of blast furnace slag with 0% conventional aggregate. So it is completely a non-conventional concrete. So we have these 2 ends of the spectrum, and in between we have 50-50, a combination of aggregate and the slag, and we have another composition wherein there is a predominant amount of slag with some or 25% of the concrete. Now when we measure the compressive strength of these different grades of concrete, we find that the concrete with 50-50 slag and aggregate has a strength that is equivalent to that of concrete with 75% blast furnace slag. So when I have a concrete that predominantly comprises of blast furnace slag, 75% of it, its strength over different days, 7 days, 28 days and 60 days, is equivalent to that of the blast furnace slag that has 50% aggregate and 50% slag. So the concrete with 2 different composition of slag and aggregate gives us almost equal compressive strength. Now when we compare that compressive strength to that of pure concrete with exclusive aggregate present in it, with no traces of blast furnace slag, we find that the strength is not significantly different, it is comparable. So what it essentially means is, of course I cannot have a concrete with complete blast furnace slag in them, with no aggregate present in them, but on the other hand, it is possible for me to have a concrete with significant amount of blast furnace slag present in them without losing much of the comparative or compressive strength rather. So at the end of the day, it is proven by this particular study that a significant portion of the aggregate can now be replaced by the blast furnace slag without losing much on the compressive strength. So this is one primary application of our crystalline form of the blast furnace slag. Now when you consider the amorphous form, the glassy form of the blast furnace slag that is produced by water cooling, essentially quenching, if I may say, the application of this form of the blast furnace slag is replacing one other component of the concrete, that is cement. Now while the crystalline blast furnace slag replaces aggregate in the component, or in the concrete rather, the amorphous blast furnace slag replaces cement in the concrete. Now this has a wonderful hidden advantage, primarily because the way cement is manufactured is an environmental friendly process, because when you consume a greater amount of cement, it means we are required to produce huge amount of cement, and the conventional way of producing cement is not an environmental friendly process. So now if I have a way to reduce the cement consumption, what we have essentially done is we have found a way to reduce the production of cement, thereby making the construction process environmental friendly. So that is essentially what using the amorphous or glassy blast furnace slag does. Now if you consider the production or the manufacturing of the cement, this is rather the primary reaction that is responsible for it. So what you do is you take a mixture. So if you consider just a skeletal view of the manufacturing of cement, what you essentially do is you mix up lime with that of clay, and then you heat them to high temperature. And when you heat them, they essentially break down chemically and ultimately form something called as a clinker. And when this happens, you generate enormous amount of carbon dioxide, which is something we have to avoid in the days to come. So therefore, if this is the conventional process, and if this is what using cement demands, now if I find a way to reduce the usage of cement, so essentially indirectly I'm contributing to reducing the amount of CO2 that is getting generated. So if you see in this article, it is explicitly stated that the CO2 formation is one of the primary factor that is responsible for increase in the CO2 content, or rather the cement production is the primary factor that is responsible for, or one of the primary factors that is responsible for the increase in CO2 content. So essentially, as I want to expand the city, I am in a way expanding the amount or increasing the amount of CO2 that is let out in the environment through the cement manufacturing. Now we have a way to reduce them. So there is this wonderful paper here. Yeah, in a way wonderful. I hope to do an entire session on that paper. So this paper compares the future of how much carbon emission is going to be primarily from that of the cement industries. So the focus is on the amount of carbon dioxide that is going to be let out when we exclusively focus on the cement industries, and particularly in developing countries. This paper, the reason I have a mixed feeling about this paper is primarily because this paper is published by or is authored by scientists from China. Even though they concede that when compared to other nations, China is sort of a developing countries, I don't know, for some reason, they choose to ignore information or data from that of China. So you have a paper authored by scientists associated with China, scientists from researchers from universities in China, and they are collecting or analyzing the amount of carbon content that is going to be released by the developing countries. For some reason, they leave China out, but the country they consider as the prominent developing country is India, and they say that if we follow what we are currently following, that is business as usual, if we do that, this is going to be the amount of carbon content we are going to let out. And if we follow the global average, and it seems for some reason both global average and our business as usual are the same, and it seems the China level, if we want to achieve the China level of expansion, then it means we will be letting out more amount of carbon dioxide. And if you want to follow, or if you want to raise our progress to that of the developed nation, it means we are going to increase the amount of carbon dioxide we are going to emit. So essentially what it means is the development of a nation, if we tie it up with the development of the cities, so if we want to have the cities that are similar to that of what they call it as China level, or if you want to have cities something similar to that of the developed nation, if India wants to achieve that, it under current trend can only do that by increasing the amount of carbon dioxide. Of course, there might be some concerns, the geopolitical or that of the environmental concerns, that could prevent, or you can cite this article to say that okay, maybe it's time for us to slow down. It could happen, but nonetheless, what this article says is if India wants to progress at the rate of China or that of the developed nation, according to this article, it means it will ultimately end up increasing the amount of carbon dioxide in our environment. Now, one way of doing that without achieving these levels, or let's say the developed level, without increasing the amount of carbon is here. So when we replace the cement significantly with that of the blast furnace slag, particularly the glassy blast furnace slag, so we will be able to achieve those levels or that level of the developed nation without increasing the amount of carbon dioxide, without contributing significantly to the carbon dioxide emitted to our environment. Now this is what is rather being projected. So in the days to come, at least in the developed nations, the amount of CO2 can be reduced by using this blast furnace slag. And if I want to wind this up, the application or the management of the blast furnace slag, so we have to consider the final form of the blast furnace slag, that is that of the granulated blast furnace slag. And as you can see here, this granulated blast furnace slag can be used to replace almost all components of the concrete, of course, except for the water. So that is exactly what you see here. Even in minimizing the amount of CO2 released, we can use this granulated blast furnace slag. So that the reason why the granulated blast furnace slag is sold in market, not the glassy or the crystalline one, is primarily because this can be used to replace both cement. Depending on how you process them, they can be used to replace cement. They can also be used to replace our aggregates. So all the major components except for the water, the whole story there, except for the water, we will be able to replace it with the granulated blast furnace slag. So ultimately, using blast furnace slag helps us get into the circular economy component. Secondly, that is it is helpful for the economy, and also it's helpful for the environment. And specifically, if I'm able to replace cement with that of the glassy blast furnace slag, it would rather reduce directly the amount of CO2 that is let out in the environment exclusively by the cement manufacturing units. So these are rather of the primary management way of the blast furnace slag is through the construction, and we now know where exactly in construction can our blast furnace slags be deployed. Now, in the subsequent session, we are going to get into rather technically more rigorous application of the blast furnace slag. What we are essentially going to do is we are going to tackle the existing waste with the blast furnace slag, which in itself is a waste. So we are going to let the blast furnace slag, which is a metallurgical waste, to manage the existing waste. So that is what we will look into in the upcoming session, and this is going to be rather more technically rigorous than what we have considered so far. Goodbye, guys.